Hello, guys. So welcome back to our class again. So first, any questions from the last lectures?
Nope.
Okay.
Hey, Professor.
Yes.
I have a question on, I think, the homework that was assigned. For the part that we have to fill in, are we supposed to just update route with the position of the nodes in between the start and the end node?
Yes.
Okay. Thank you.
So for example, if you have, for example, 5 nodes in between the start and the goal, okay, you just put these 5 nodes in the route. Of course, construct an algorithm, some coding that finds this shortest path. It's not just any path, okay? It should be the shortest path.
Okay.
If for the breadth first search, it needs you to think a little bit because you need to fill this fourth column that I mentioned last time. Today we're gonna take the depth first search. Okay, again I will do the same, just like breadth first search. I will show you the idea, the coding, but then for the shortest path, I will leave it to you.
Okay.
We may give you some hint, but most of the work will be yours. And both assignments is due next, I think, next Tuesday, 1 p.m.
Next Tuesday, 1
I can't remember.
Okay.
I will
Thanks.
do it 2:30. That's fine. I will do it as 2:30. I will change it.
Okay.
Okay.
Thank you, Professor.
So we
also had a question.
Yes. Continue.
For that fourth column, is that absolutely necessary, or can we just do it like another way?
It's
because I kind of did it a different way. I went from the goal node to the start node instead from the start to the
don't
goal.
explain anything. Don't explain that. Don't explain that. Okay. So you did it in a different way, right?
Yeah.
And you are sure it's a correct?
I mean, for the examples, it works. All the examples that you provided.
Yes. It works, right?
Yeah.
And it was the shortest path?
Correct.
Okay. So submit it. I will read your code, but please comment it very well. Very well, okay? And if I didn't understand it, I will, of course, call you for a meeting or something, okay?
Okay.
Your name is Saul. Am I pronounce it right?
Yeah, correct.
Okay. Any other questions? Okay. So last time we finished Brett's first search and it's coding in MATLAB. We will do the same here for depth first search. Okay. I will also show you the differences that I talked about between breadth first search and depth first search. Okay. And the basic one is that depth first search is not guaranteed to find the shortest path. It will find a path. Okay. It will be good path, but it's not always the shortest one, okay? So you guys see my screen, right?
Yes.
Okay. So as we said, for depth first search, we take a node. Oh, this guy is not. We take a node, okay, and always start from this node. Once we find another node, we start from this another node, okay? And you know, so you take an option and just go deep in that option until you finish all the possibilities that come out of this option. You may find the goal, or you may not find it. But at least if you didn't find it, you are 100% sure that this path, this option, will not lead to the goal. Okay? I mean, you get a full information about what's gonna happen if you take this path. This is good for depth first search. Yes, it's this kind of criteria may not lead to the shortest path, but it gives you some extra information that you can't get from breadth first search, or it's not guaranteed to be, you know, to get it from the breadth first search. Okay. So let's do the same again. I'll just recap very quickly here. So from the start, we want to go to this goal. Okay, this is our priority: up, right, left, and down. So we go up, we landed here. So we just forget about the start and we start from the node that we just reached. So we go up from here and we can go up. This is a free cell. And then we forget one and start from 2, 3, 4, 5. We get the goal in just 5 steps. And we said that that doesn't mean that it's better than depth first search, because we show another example in which depth first search takes 34 steps, while breadth first search take only 29 steps. Okay. Now let's see another example. Again, we have up, right, left, and down. So we start from here for up. This is number 1. 2, because we start from the last node we reached. This was 1, so we start from 1. And up again, we have 2. From 2, we go up again, 3. From 3, we go up again to 4. From 4, we go up again to 5. From 5, we reach 6. And here, there is no up because it's outside the map, beyond the map. There is no right because this is an obstacle. But we have left, so we go to 7. In 7, we can't go up. It's outside the map. We can't go right because this is already explored. But we can go left. So this is 8. In 8, we can't go up outside the map. We can't go right because this is explored or visited. We can't go left because this is a wall, but we can go down 9. And from 9, we can't go up. This is visited. We can't go here. Obstacle, but we can go down to 10. And you reached the goal. So you're finished. But let's have a look here. These are all we know from our map. These are only the nodes that we visited, explored. And based on these nodes, we're gonna construct the shortest path. And clearly, this is not the shortest path. The shortest path should be something like this. Maybe like this, or even like this, okay? Or even like this, or maybe even like this. whatever. All these paths that I'm showing in here takes exactly the same number of steps, which is less than what the depth first search gave us. So we take 1, 2, 3, 4, 5, 6. But for depth first search, what it gave us, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 40% extra length. And the reason behind that comes from the fact that when we explore a cell from a frontier, the frontier in depth first search is not guaranteed to have less distance to the starting node. So I will mention this clearly now. Maybe write it again. In breadth first search, when we explore a node from some frontier, always distance of the frontier to start node is less than the distance of this new explored node to the start node. And this is not guaranteed in depth first search. That's why it's not guaranteed for you here in depth first search to get the shortest path possible in a map. Let me do that again, this kind of writing. Let me do it with example. Okay? Let's remove all this stuff just to make it clear for you guys. Yes. Okay. Good. So we reach it for depth first search in here. We reached the goal from node 9. Okay. And what is the distance between this node and the starting node? Let's count. 1, 2, 3, 4, 5, 6, 7. So 9 was the frontier from which we explore the goal node. The goal node itself has 6, the distance of the goal node to the start is only 6. So this condition here that is always being satisfied in breadth first search is not satisfied here in depth first search. Because here clearly the frontier from which we explore the goal node had a distance to the start larger than or greater than the distance of the goal to the starting node. Its distance is 7, this distance is 6. If you do the same example using breadth first search, you will find that you will explore node 10 from here. Let's make it with another color. Yes, from this node. That's why you will find the shortest path. I will leave it to you, okay? And you will find that we will explore node goal from this one. And this one has a distance of 5. Not in breadth first search. The frontier from which we explore the goal has distance of 5. And you will find that it may be like this, the shortest path, or like this, or like this, whatever. I mean, it's in that area here. Whenever you are in that area, you have the shortest path. Okay, so now let's go ahead and talk about the coding nodes. So again, we will do the same stuff in MATLAB. Luckily, yesterday when I do the coding for depth first search, I searched again for the, I know there is no stack, or queues in MATLAB, but I found a guy, okay, that do, a module, a function, okay, in MATLAB for the stack and the queue, the FIFO, I mean, okay. So you can use this function as your stack, okay. Remember we said that we need FIFO in breadth first search, but we need stack, first in last out, or last in first out in depth first search. Okay, so I used this neat code in MATLAB. It's very nice. I will show you the code right now. Okay, but before going to the code itself, so the good news is that we're gonna use a stack, which will make the coding very easy for us. Okay. So how we gonna use a stack? Let's do exact, explanation for this particular example in front of us, this mapping here, okay, using the stack. So let's change this color to red, for example, whatever. Although it is not good, but So we will have a stack. This is our stack, and we start to fill it and read what's in the top of the stack and try to explore it. So basically, the first node, so this is the start node, this is the goal node, and we want to use depth first search to reach goal from the start. So the first one we're going to add is the source node, or the start node, I'm sorry. Okay, and we have the same roles again, up, right, left, and down. This is our priority all the time. Of course, you can change it, and I will show you when we code in MATLAB that if you change this the priority, you might get faster to your goal. And remember, this is maybe good for depth first search, because in depth first search we take some path and continue in that path forever until we reach, even dead end or the goal. We explore all the possibilities. So you might have an idea where is the goal is and set your priority based on that to get there faster. Okay. So we're gonna start by the start node. Can we go up? No. Can we go right? Yes. So this is one. Of course, this is not the real ID of the node. As we see in MATLAB, each cell here has its own ID. Okay, but since we know between us that in each step we explore a different node, so each node has a different exploration step. So it's a unique number. So we can use this number as an ID just between us. But in MATLAB, no. This node here has its own ID. But we will explore it at step 1. That's for sure. Okay, so now this is the head of the stack. So we will start from it. Can we go up from 2? Yes, we can go up. So we go to 2. Now 2 is the head of the stack. So we're gonna start from 2. Can we go up? Yes. And each time we push into the stack. let's draw it a little bit, just to not to mix with the writing. So we're gonna make it a little bit. One, two, three. Now we are at 3. At 3, can we go up? No. Can we go right? No, but we can go left here. So this is 4. We start from 4. Can we go up? Yes, 5. And I forgot something in here. So we need to make an array. It's called the visited node array. So until this moment, we visited S 1, 2, 3, 4, 5. This is really important, as we will see later in this example, and of course in our MATLAB coding. This is 5. From 5, can I go up? Yes, 6. So I visited 6. Can we go up? Yes, 7. Visited 7. Can we go up? 8. We visited 8. So each time you add something here in the stack, you add also in the visited, because it's visited. Can we go up from 8? No. Can we go right? Yes. 9. 9. Can we go up? Yes. 10. And we will have a moment here. From 10, can we go up? No, it's outside the map. Can we go right? No. Can we go left? No. Can we go down? No, because 9 is visited. So we now for sure cannot reach the goal from 10, from node 10. So it's useless node. So we need to pop up or pop this node out of the stack. We don't need it anymore because it will not lead us to the solution. So the last node we reached here is 10, and we're gonna pop it up right now from the stack. Let's change the color right now. So we make here a pop. Until this moment, all what we have done is pushing. We pushed S. So let's do the pushing with another color. I'm sorry. So we push S. Then we push 1, 2, 3, 4. All these nodes were pushed into the stack. That's why we explore them in the first place. Until we reach 10. At 10, we explore all the 4 neighbors. No possibility for continuing from 10. We cannot reach the goal from 10. It's a useless node. Just pop it from the stack. So we pop 10 from the stack. Okay, if we pop 10 from the stack, we end up with a stack like this from the beginning in here until 9. So this is now the head of the stack. Okay, use it. Now in 9, can we go up? No, because we visited 10. We has visited 10. Can we go left? No. Can we go right? Can we go left? No, also because we visited 8. Can we go down? Also no, because this is a wall. So 9 is also, a dead end. You cannot use 9 to reach to the goal. There is no hope from getting to the goal from 9. So pop it also from the stack. Another pop. So the stack now from here to here only. It's a dynamic array. The memory size in the memory will change. That's also a very good thing about using queues or stacks, because they are dynamic arrays. Okay? If they have 2 elements only, then you are using only 2 elements in the array, 2 locations in the array. If you have 1000, you will have 1000 in the array. If you use just an array, like what we have done with breadth first search, all the time you are, reserving 1000, for example, node in the array. Even if you will not use all of them. You might not use all of them. Okay, now we reached 8. 8 now is the head of the stack after popping 10 and 9. And again, the same questions. Can we go up? No. Can we go right? No, because 9 is visited. Can we go left? It's outside the array. Can we go down? No, because 7 is also visited. So we're gonna also pop 8. So we pop this, we pop this, we pop this. 7 will be the same. Pop 7. 6 will be the same. Pop 6. 5, same. Pop 5. 4, again the same. Now 3, the same, because this is not possible, this is not possible, this is visited. And this is also visited. So again, Bob 3. Now we end up again at 2. And that 2, now it's 2 is the head of the stack, so just explore around. Did we go here before? Yes, we visited this, so we cannot visit it again. Can we go to 1? No, because it's visited. Can we go right? Yes, we can go right. Okay. But now the stack, so we go here. This will be, let me draw again this. So this will be 11, because we explore this cell at the 11th step, because this is 10. The last one was 10. Where is your stack now? Your stack is from here to here only. So we're gonna put 11 just after 2, because we popped all these. I will just, so let's call this step 1, for example, or whatever you call it. So let's have a step 2 here. We have another stack with only 3 nodes. S start 1 and 2. And we're gonna put 11 in here. In 11 now, this is our head of the stack. Can we go up? No. Can we go right? Yes. 12. In 12, can we go up? No. Can we go right? Yes. 13. Can we go up? Yes. 14. 15. 16. In 16, can we go up? No. Can we go right? No, but we can go left. 17. In 17, can we go up right? Yes. So 18, 19, and just don't forget to put all these nodes in the visited. So we have here 11, 12, 13, 14, 15, 16, 17, 18. I'm sorry, I just forgot to put them. So we have 19 here. In 19, can we go up? Yes. 20. 20. In 20, can we go up? No. Can we go right? Yes. 21. 21. Can we go up from 21? No. What is this? No, we can't. Oops. Anybody here has a question, guys? I see you have chatting, some chat. If you have questions, just ask me. That's fine.
Professor, are you going to put up the PowerPoint for this slide, for this lecture?
Yes, I will. I will. Just after the lecture, I will share you the PowerPoint. This PowerPoint has both breadth first search and depth first search.
Okay.
But if you have a question, please ask me. You can say, hey, Mustafa, I completely messed up. I can repeat. That's fine for me. Okay. So at 21, we can't go up, but we can go right. So 22, add it here in the visited, and add it here, 22. Now at 22, we can't go up. There is some, yes, we can't go up. We can't go right. We can't go left because 21 is visited. Since the visited array in here, the array that we created and we add each time we visit a node. And we can't go down. So we know to the goal. So we're gonna bob 22 from the stack. So we make a bobbing here. So 22 is bobbed. Now the head of the stack is 21 again. In 21, can we go up? No. Can we go right? No, because 22 is visited. Can we go left? No, because 20 is visited. Can we go down? Yes. This is not an explored one. So instead of drawing this again, so here I will add the new node, 23. So this will be 23. And now from 23, before exploring more, as we did with Brett's first search, we're gonna check if this is the goal or not. Yes, it's the goal, so we stop the search. Now we can construct a path from the start into the goal, which will be something like this. Let's change the color. Okay. So this should be the path from the start to the goal. And what's your ending stack? This is our stack now. Start 1, 2, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23. Remember, we removed the 22. We popped it out from the stack and we put 23 in its place. Okay. So the bottom line here is two important points. We will use a stack, okay, and also we will use we will create an array called the visited nodes, and we will update this array each time we visit a node. Okay. Any questions?
Yeah, just a quick question. So
Yes.
the shortest path, so there wouldn't be a possibility that it wouldn't go from 19, 20, 21, and then the goal node, right?
You want the short space to be like this?
No, I'm saying if that's a possibility, like as in terms of like, does it always, because you know how you said it sometimes wouldn't be the shortest path to the goal node, but I'm just asking like in terms
Yes.
of DFS, it's based it on like the nodes it has explored. So from those nodes it has explored, it's getting the shortest path.
That's right. That's right. It's in-depth first search. It's based on the nodes that you have explored. Okay.
Okay.
But if you look here, you explore the nodes, all the nodes around the goal. So
Yeah,
the
yeah.
possibility of having the shortest path is higher now. Okay. In Brett's first search, it's a guaranteed. There is no arguing that. But in depth first search, if you didn't explore, for example, node 19, you will not reach the goal from node 19, although it's not possible here in that example. But anyways, so yes, you are right. It's based on the nodes that we are explored. And in that case, the nodes that we have explored can give us the shortest path, the shortest.
Okay, thank you.
The best. Okay. Okay, now let's go to the coding. But before going to the coding, any questions, guys? If you just lost, just give me, a hint. I can repeat. That's very fine for me. Okay. Okay. So let's go forward. Okay. Yeah. So let's go to the coding. And we're gonna do in the coding just like what we have done with breadth first search. Again, I have, wow, where is the, yes. So I'm gonna now share the other screen. That's right. F3 right now. Okay. So you guys can see my screen, right? I don't know what. Yeah.
Yeah, we can see it.
Yeah. Okay. Okay. I'm very sorry. I just messed up with this. Okay, so let's have our coding in here and our yeah, we're gonna put this guy beside us, so we're gonna refer it anytime. Kind of grids we have here. Okay, we can do with this grids, that's fine. Okay, can't remember which grid is this. So let's first see how using the GUI, okay, how the depth first search, searches for the codes. I will change the place of the camera just to be in front of me exactly. Okay, should be better for you because it will be in front of me. What's messing up here? That's better, right? Okay. So I will just run my code. Okay. So this is a start, this is the goal, and this is the, I don't say the max or shortest path, but the best that we can construct using the explored nodes, okay? And that's why it's not guaranteed. So let's change the map. Let's have another map. Oh, this is the same one. Oh, it's the same. I don't know what is the difference. There should be some difference. So, oh yeah, I understand. Should comment this. Okay, so this is the first map. Let's run it. Yes. So let's see what's gonna happen. Okay, guys, you see, here is the same priority, up, down, We can also make it a little slower so you can notice it better. Let's make it, for example, half a second or something. Okay. Okay, let's see another example. Comment. One comment. This is easy. Yeah. There is the effect of, you know, choosing the priority. Okay, because we prioritize right over left, it makes such, you know, very strange stuff, because he was just right beside the goal, but he deviates from it. Okay, I will repeat it again to see why it's so. Yes, until we reach that one here, then it goes right, because we prioritize right over left. If we do the opposite, it will just stop here and go to the left and find the goal, and that's it. Okay, let's do it. Let's change. So let's stop this guy. We'll just finish now. So okay, good. It's finished. Let's change the priority. Let's make right over left. Okay, so we can just make like this. Yes, and change here n equal to 2, n equal to 3. So if n equal to 2, I will explore my left. If n equal to 3, I will explore my right. Okay, so let's do it and see what's gonna happen. Good. So here, that's what I'm saying. Up, down, left, right, this priority, because you take some action or take some path and continue with all the possibilities in that path in depth first search, knowing, you know, where is the goal knowing where the goal is. Okay, you can customize or choose your priority such that you reach there faster. Okay, and that's one example for this. Okay, let's see other examples. Then we will delve into the code. One comment. This should be an easy one. Yes, this is very easy. Okay. Okay, so let's have the last one. This is the one that we have just, you know, present in the presentation. Okay, so let's now, you know, explain this code for you and fill out the missing, because there is missing. So let's go to the this guy. So these two guys here has class name and class grid. So these are the two files that I sent you, in which the path part, constructing the shortest path, is missing, and you should complete it. Okay, so again, like what we have done with spread first search, we are construct first. This is the main. Yes, it's a map. Yes. Okay. So basically, we first initialize this map, all of it to false. Okay, false means free. Then we mark the obstacles with true. Okay, and what kind? Yes, we are talking about this one here. So we have all the first column is obstacle. So this means all rows and one is the first column. So all cells in the first column will be marked by true. This means all. This column means all. Then cell 1 and 5 is also true. This one, it's the first row and the fifth column. Then the cells those two cells, this one and this one, at the 10th row, and the second and the third column is also obstacles. And then we have these two here that really spoils everything in depth first search and make us go to the goal using, longer path. Is at rows 2 and 3, from 2 to 3, and they both at the column number 3. And this is the starting node at 7th and 4th column, and this is a goal node at the 3rd row and 2nd column. Okay, and this is again a variable that we control. It's a Boolean variable, and when we set it to true, then we will see some GUI. If you curious about the time, set it to false. Just make it false instead of true. Okay. And then we call our function, which I call here DFS class grid. Grid because this is a grid. It's not really a graph with a conventional idea. Also, any grid is actually a graph. Okay. So good. So let's go to this function. And in MATLAB, function should be in separate files. Okay, and the name of the files takes the name of the function, and it's also .m. And MATLAB, magically will know that this is a function and mark it with f as a function, f of x. You see this f, little f. So this means it's a function. It's a function file that will be called from another file. And one thing I forgot here, just to be before, okay, yes. So I told you that I found a function that a guy somewhere has already implemented, and this function, implements a stack for you. Okay, you just need to call this function within your code, and that's it. I will show you the link for that function. I hope I am lucky and find it. Yes, here is the link. Okay, let's post it. I will post it after the lecture. So this is the link to the function. You can just download it. Okay, it's a big file because this file, I think, no, it's 3 files. One of them is implementing something called the list. We are not interested in list, and the other one is implementing a FIFO which we can use, for example, in the breadth first search. As far as I know, I didn't experiment with it, but I think it's a FIFO. And the last one that I used is a stack. Okay, good. So this stack file or this stack function is actually, let's go back to our codes. Yes, this stack function is this one. Okay, just put it there. If we look at it, we'll find some very complicated code that we just ignore it. But it's very easy to use, and how we can use it, just read these 10 lines, yes, those 10 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. Okay, or 9 functions. So basically, if you wanna create a stack, okay, you just give it a name. Here it's called S. You can name it whatever. Called C stack. You must call it. This is the name of the function. So whenever the MATLAB finds this keyword, it will look at this file here, C stack of C. And C is just the number. It's an initial number that you're gonna push into the stack. For example, if you write S equal to C stack of 1 or 2, whatever, of 1, then you create a stack called S and you push 1 to the first location in this stack. If you want to know the size of the stack, how many elements inside the stack, just write the name of the stack dot size. If you want to know if the stack is empty or it still have some elements, just write this s.isEmpty. This is a function, it's a Boolean function that returns either true or false. If it's true, then it's empty. If it's false, then it's not empty. If you want to delete all elements in the stack in one step, just write this line of code, s.empty. If you want to push a new element, so you just write push, two parentheses, and put here the element that you want to push, 5, 6, whatever number you want. If you want to pop, take out the head of the stack, just write s.pop. If you want to read, only read the head of the stack, just write s.top. So this will read the head of the stack without deleting it. It's not like pop. Okay. Then we have s.remove. I don't really know the difference between s.remove and s.empty because they look like the same. But maybe s.empty means it's even, you know, remove this whole structure from the memory. Maybe. But we are not interested in that. Okay. What we're gonna use basically here, we're gonna use this guy, of course, because we wanna create a stack. We're gonna use this. We're gonna, of course, use push and pop and top. And for some debugging, we're gonna use content. What does this one do? It's actually return all the data inside the stack. So you can, for example, if you wanna be sure that, oh yeah, this cell, I'm not sure the algorithm should explore this cell, but I'm not sure if it's explored or not, just print out this s.content, and you can see if the cells that you have some doubts about is in there or not. Okay, good. So these are the functions that we're gonna use, or most of them. So let's go back to here. Yes, yeah. Again, we have this stuff for the GUI. We'll create a map in order to show it as an image. Okay, and again, this map should have numbers, and these numbers should refer to the colors here. Okay, 1, for example, means white, 2 means black, and so on and so forth. Just this beginning, this start is just like this first search. Okay. Again, here mark any free cell with 1, which is white. Mark any obstacle with 2, which is black. Then we get the start node and the goal node IDs. Okay. Because it's easier to use the ID of the cell rather than its coordinate, column and row. And we mark the starting node with green because 5 is green. This is 5. And we mark the goal node with 6, yellow. We need to track the steps at which we explore each cell. So we create a variable called step in which we will, you know, increment each time we explore a new cell. Okay, we need array to mark if the node is visited or not. Okay, if the node is located in the array, then it's visited. We cannot visit it more. If it's not, then we add to the stack and add it to the visited frontier array. Okay, and we start or initialize this visited frontier using the start node. Because this will be, you know, the node that we will start with. Here, this one. And then we create the stack. This is the frontier stack. Because each node pushed into the stack will be a frontier by default. because whenever we push something, we start from this cell. Whenever we push a cell, we start from it. Good. So here we create a stack. This is a function. So whenever MATLAB sees this, we'll go to this file. Whatever happens there, it's a magic. We don't care about it. We just use it. Okay, and we'll initialize, or the first element, or the first cell, or the first ID that we're gonna push there is a starting node ID. Okay, good. So now we have a stack, and this stack has one element, which is a starting node ID, the ID of this cell, whatever the ID is. Okay. Then we go into the infinite while loop, just as Brett's first search. Again, we draw, and we're gonna be sure that the start is green and the end node is yellow. So each time you make this, tedious step, but just to be sure, and draw the maps that you have right now. Okay, now let's fill in. In any loop, in any iteration, we want to read the frontier node to explore. And where is our frontier? Where are our frontiers? All our frontiers located in the stack. It's called the stack. I call it a stack. Okay, just to make it very easy for you and for me as well to comprehend what it is. So we want to read the top of the stack, but we don't want to remove it. Because if you remember, when we explore some node, we for example, start with up, then go up, we may go back to the node, the same node, okay, to explore other possibilities. Because when we go up, for example, it was a dead end. We didn't reach the goal. Good. So to do that, we're gonna use stack.top. So this will give us, or return to us, the top of the stack, the head of the stack, which is currently the starting node, without removing it. It's not Bob. Then we're gonna check. If the current frontier is the goal, we must break the loop. We have reached our goal. So if the frontier node, which is this guy in here, equal to goal node ID, and we have the ID, I think. Yes, we have the goal. Yes, we have the goal node. Yes. Then we break. Okay. If it doesn't, then we should continue and explore. Okay. Now this is for the GUI. Any node, any frontier that we're gonna explore, we mark it with red, and red is number 3. Red is number 3. 1, 2, 3. So we're gonna put here 3. So map of frontier node is equal to 3. So let's now explore the frontier neighbors. It's easier now to use the coordinates. How we get coordinates out of the ID? We know the idea here. So we use this neat function in MATLAB called index or to subscript. And subscript here means the X and Y. Or I'm sorry, the column and row. We put here the size of the input map. Remember this guy here, this function returns the number of column and the number of rows in the of input map or map. You can use both because both are the same. And the node ID. Then we get here I and J. I is the row number of the frontier node, and J is the column number of the frontier node. Good. Now we explore all the neighbors around this node, around the frontier node. So we have a for loop from 1 to 4, because possibly we have 4 nodes before 4 neighbors. Any cell has 4 neighbors. This is our priority: up, right, left, and down. You can play with this based on the location of the goal to your start node. Good. So if we agree that we're gonna use up, right, left, and down, so if I wanna go up, then the upper node, the node above me, has the same column. So here column will be equal to J. Column is the column number of the node of the neighbor, of our neighbor. But the row will be -1, because, for example, this is S, this is at row number 7. The one above it here, it's at row number 6. So what is the row number of the frontier node? It's I right now. So we're gonna subtract one from it. The node on the right of me, for example, from the start here, this is the right of me. It has my column +1, the frontier column +1. This is column 4, this is column 5. So I need to add 1 to the frontier column. A frontier column in this case is J. And the row should be the same row. So same I. The column on the left of me, again the same row, but now it will be J -1, just like Brett's first search. Nothing new. Down, it's like up. So same column, but now row +1. So this node here has a row of 8. This is 7. So it's 7 + 1. Good. We need to check if this node is inside the map. If it's outside the map, then we're gonna explore another one. We just skip all the remaining steps because it's not valid, and go and increase n by 1 to explore another neighbor. Okay. So if row, and the condition is that the row should be between 1 and 10 in that case. So it should be between 1 and 10. But here again, we do it in the opposite way. We see if we have a violation, we skip. Violation means row is less than 1, or, and this is or in MATLAB again, or the row is larger than 10 in that case. And again, if we put it 10, then we this code will be customized only for that particular map. So we're gonna here write size of map, and remember, size of map will return two things: the number of rows and the number of columns. And the number of rows is number 1. So we wanna the first output. We don't want both. Okay. I will leave this for a moment. We'll go here for the column. So if the row is less than 1 or larger than the size, the maximum size, which is 10, I'm gonna continue. I'm gonna skip. Here again, but for the columns should also between 1 and 5 in that case. So if it's less than 1 or larger than 5, I will skip and make a continuing. Okay. So less than 1 or larger than the number of columns in map. And the number of columns is size of map, but number 2, because Size of map alone brings you back or returns two numbers, the number of rows and the number of columns. And we need the second one, which is the number of columns. Now, what is this? Why I am doing this? So I am saying here basically is that if node is less than 4, then you will have other possibilities. Then when you continue just to go to the beginning of the loop, the for loop, and increase n by 1 and explore another neighbor. But maybe this node, okay, is a dead end. So we can't reach the goal from these nodes. You remember when we make a pop, okay, all the nodes that popped out from the stack, as we see in the examples, these nodes were dead ends for us. Meaning we can't reach the goal from these nodes. We explore all their neighbors, but we can't reach the goal. So in that case, I need to pop up this frontier, because this frontier right now that I'm exploring around is a dead end. So here I will make a stack dot pop. And what is the head of the stack? The head of the stack is actually the node, the frontier node that I am exploring right now. So if I pop here, that means I am popping or removing the head of the stack or this frontier. Because this frontier, I have explored all its 4 neighbors, but nothing valid. That means I can't reach the goal from this frontier. So I must pop it out and go to its parent, we can say, and explore its parent. Maybe his parent has, you know, other possibilities. And at that time, I should break. I should break the for loop. Because I finished exploring. I explored the 4s, okay, the 4 neighbors, and no, you know, no value, no benefit. It's dead. So again here, I will put stack.pop if n is equal to 4. So if n is less than 4, I can go back to the for loop and increase n and explore another neighbor. But if n equal to 4 and I found myself that this guy, the current neighbor, is also, so it's a 4th neighbor, is also not valid, then this frontier cannot lead me to anything useful, cannot lead me to the goal. So I must pop it out. So I did this if condition. Okay. I also want to skip if I reach the barrier. If I am, for example, here and I explore my right, it's a barrier. And we know that for any barrier cell, it should be with 2 in the map or 1 in the input map. This is what we know from Brett's first search when we put it together. So I can say here, if input map of neighbor and remember input map has true or false, so I can just write it in that way. If input map of neighbor is false, that means it's true. I'm sorry, it's true. That means it's an obstacle, so I must skip it. Okay, but again, if this was the 4th neighbor, then that means that all the neighbors of the current frontier is not valid, okay, and you can't reach the goal from that frontier. So you must pop out this frontier from your stack. So I make here a condition: if n less than 4, then there is a possibility that there is a neighbor that has some way to the goal. So in that case, I make a continue. So go to the for loop again, increase n and explore another neighbor. But if n equal to 4, then this frontier is a dead end. We can't continue from this frontier, so we must pop it out. The last check that I am doing to any neighbor cell is that this cell is visited before or not. And we may, as you remember, we made or we create an array called the visited frontier. Okay. So if this neighbor located in this visited frontier, then we should skip. And again, if this was the fourth neighbor, then you should also pop out this frontier from the stack. Okay. Once we pass all these three and reached this line here, then this neighbor wasn't explored before. Nobody has visited this cell before. So we can add it to our stack. And of course, our visited frontier array. We need to know the number of steps we reached so far, so we update the step. So this will be step equal to step plus 1. And the MATLAB doesn't have this neat feature of C++, which is step plus plus. It doesn't have this, for sorry, but anyways. Okay. Now we need to push this new node, this new neighbor that we discover into the stack. So basically we're gonna push it. So we did this stack.push. And we put here what? The number that we want to push into the stack, which is neighbor in that case. The neighbor ID. Remember, we get the ID in here. So we have the ID. And we need also to add this ID, this new ID, this node to the frontier, to the visited frontier array. So if you want to just add one element to an array, you just do it in that way. So neighbor equal to the previous neighbor and add this new entry to it. It's also dynamic array here. So whenever you add something, you just put the new, there is no fixed length for frontier based frontiers. You just add the new element in that way. That means the new frontier array is equal to the last frontier array added to it or concatenated with the new neighbor ID. This is also a very neat property in MATLAB that you can just add an element to dynamic array in that very easy way. Then we're gonna draw, okay? We're gonna mark this visited neighbor with blue, and the blue is 4, and we wanna make sure it's not our goal, and our goal is yellow. So if it's yellow, then we just keep it yellow. Don't mark it with blue. That's it. That's why we put a condition here. Okay. But in general, any neighbors that we visit, we mark it with blue, and the frontier with red. Then we draw the map again. That's it. Then, and that's different from or differentiate between DFS and breadth first search, BFS. This simple line here. In BFS, we continue. This is, by the way, the end of the for loop. So in BFS, there is no break, and we just gonna continue with the for loop and explore all the 4. But here in DFS, once you find a valid neighbor, a neighbor that is not visited before, it will be on the top of the stack, and you should start searching next time from this neighbor. That's why we break here. Please don't continue exploring other neighbors, because we already have a good neighbor, we can say. Okay? So we break the for loop, and you know, this is again similar to, we go back to the while true loop, and this is equivalent to the last conditions that we put for BFS, in which we are, you know, checking if there is a route or not. Okay. Here, if you remember in breadth first search, if the frontier pointer is pointing to an arrow in the frontier array which has invalid elements, which is infinite, that means we have no more frontiers to explore. So there is no route. Here we have the same. If your stack has no elements, you didn't add something new to the stack, that means you don't have a route to the goal. So just break the while loop and, you know, go here and return an empty route array. So we check here if the stack is empty, and if it's empty, that means there is no frontiers to explore, and we didn't actually discover the goal or explore the goal. So there is no route. Because if we explored the goal, we should break the loop here in that specific step before that. Okay? So that's basically the breadth first search. Okay? Now, so this will conclude the while loop, in which, or the exploration phase, we can say. Now, the second phase, which is constructing the shortest path based on the nodes that we discovered. It might not be the ultimate shortest path like the one we get usually with breadth first search, but the best we can do with depth first search is use the nodes that we explored and try to construct the shortest path based on these nodes. Okay. So in the assignment that I published today, you should put your code here, and again remember to mark these cells with gray, which is 8 in the color map. Okay. Put your code here. You're gonna use the nodes located in the stack. So here is the step that, you know, that reads all the content of the stack. So here is a bad thing about this stack. I'm sorry for the time, and this is the last thing. The elements of this stack has a type called cells. Okay, you don't care about the, give no attention to this new type, which is called the cells. Okay. So this function here called cell to matrix will just, you know, convert this stack, this queue, into a normal array or matrix. So this explored nodes will be just, you know, a vector or array with all the nodes from the start to the goal location. Okay, so just use this guy here. Just use this explored, it's just a normal array, just like any other array we see so far in MATLAB. Okay, and just forget about this step. You just take this guy here, explore the node, and use it in here between these two lines to construct the shortest path between the start and the goal location. So that concludes depth first search. So any questions?
Professor, so for the DFS assignment, basically we also need to include the C stack in order for it to work.
For DFS, you will not use in the DFS assignment, you will not play with this code anymore. I mean, the exploration phase, you will not change it. Okay, you're gonna just use this one here, this array here inside this between these two lines. It's not like the breadth first search. In the breadth first search, you have the fourth column that I said that I mentioned. Okay, so you must change in the exploration phase coding, and you will also put your coding here in the shortest path construction phase. But here, luckily, we're gonna only play between these two lines. We will not, we shouldn't use any or modify any code other than between these two lines.
Okay. All right.
Okay.
Thank you.
And you will find yourself, if you get the right idea, you don't need the stack, because you just need the content of this stack, all the elements of this stack, and all this element now is in explored nodes. Okay, so you're gonna use this array between these two lines to construct the shortest path.
Okay. Thank you.
Any other question? Any other question? So one last thing before you leave, guys. So I want to show you the dead end. How this condition works. So I have here a map. This is the last thing. I have here a map with no way between the start and the goal. Okay. So if we are right, then we should stop here. Yes. The rest, of course, is a solution. I will not show you the solution. So we should stop here. Should break here the loop and stop here. So let's see that. Change folder. Of course, it's just exploring because it cannot go beyond the black obstacle until it reaches a point in which there is no more point to explore. Okay. And finally, we reached this. We're gonna break, continue. So the route is just an empty because there is no route between the start and the goal nodes. Okay. Okay, that's all what I have. If you have any question, just prepare it for next time on Thursday before we start in another graph search algorithm. It will be Dijkstra, I think. Dijkstra, yes. Okay. So yeah, that's it. Thank you very much.
So both of these assignments are due on the 8th?
Right. Yes.
Okay.
Professor,
Yes.
do we have a lab on Monday? We have a Labor Day that day.
Yes. I think I sent a message. I don't remember. So because of the Labor Day, it's a holiday, so this lab will be. But even if we have a lab, we will do also coding, just MATLAB coding, because looks like the stuff of the kids will take much longer than what we expected. So I submitted all the paperwork. I finished from my side. I don't know what those guys will do afterwards. They should make a drive-through event for you. They should ship the kits we have only 4 students out of Bakersfield. They should also ship these kits to them, these four students. But I did all the required from my side. I will email Dr. Melissa today to check with her, but I believe, or I think maybe within these 2 weeks, we will have the kits. The kits will be delivered to you, but there is no guarantee for sure. But unless we have the kits, I will use the Monday as as a session, just like the lecture. Okay.
Okay, thank you.
Any other question? Okay. Thank you very much. Have a great day, guys. Bye-bye.
Thank you.